Okay, I'm going to try to do this in one fell swoop. This is, I mean, you can see which problem it is, right? Okay, so the derivative of a function is defined by this piecewise defined function, and this is a picture of it. It has x-intercepts at x equals -2, so it does hit the x-axis there, and x equals 3 natural log of 5/3. It's right there, all right? The graph of g on -4 to 0 is a semicircle. That's g, right? And f of 0 is 5. F of 0 is 5, so that's important, right? This is the derivative. The original function has a point at 0, 5. I know that for a fact. I'm just going to make a little note of that. You're seeing this in real time. You're seeing me think this through. So there's a point there at 0, 5 on the original function, which we don't know what it looks like, right? Okay, so let's have a look. A says on this interval here, find all values at which the graph of f has a point of inflection. Okay, now keep in mind, we don't know what f looks like, right? We know what its derivative looks like, we don't know what it looks like. So this is what's happening in your brain. Inflection point, oh, that's when the second derivative switches signs, okay? Well, this is a picture of the first derivative. So the derivative of this is the second derivative of f. So where would the derivative of this picture switch signs? It's where this picture goes from increasing to decreasing or from decreasing to increasing, okay? The points at which that occurs are at x equals -2 and x equals 0. Have a look. At -2, whoop, boop, it switches, and at 0, boop, it switches as well. So for A, you're going to write these 2 points, and you're going to say, these are the points that the second derivative, okay, of double prime of x switches signs. And you're done with that. Okay. B, find f of -4. Okay, so think carefully. We don't know what f looks like. All we know is that it has a point at 0, 5. Okay. This is the derivative, though. So keep in mind, we can look at area under the curve to get this. So f of -4, right? We're sort of starting at 5, and now we're moving backwards. So we're looking at how much area we pick up. But to figure out what f of -4 is, we start here, we're starting at 5, and we're moving backward, zoop, like this. So the question is really, how much space do we pick up? And in this case, it's losing space because it's positive space, but we're moving backwards. So how are we possibly going to figure out the areas of those? Well, this is a semicircle, right? So if that is in fact a semicircle, think about it for a second. Let's find the area of the semicircle itself, okay? It's got a radius of 2, we can agree with that. So the area of the entire circle would be pi r squared, which is 4 pi, okay? So half of it is worth 2 pi. So this area in here is worth 2 pi. Now look at this entire rectangle. This entire rectangle is pretty clearly worth 8. So this dark shaded region is worth 8 minus 2 pi. Now be careful, right? We started at 5, we're losing all of that. So the answer should be 5 minus that area, which is 8 minus 2 pi, which equals 5 minus 8 is -3 plus 2 pi. So that is f of -4. Okay. Now f of 4, same sort of analysis, it starts at 0, 5, and now we want to know what f of 4 is, so we pick up all this area, then we lose all that area, right? So let's figure out what those areas are. Okay, so here's what the function is, okay? We already know, they flat out told us that that point right there is at 3 natural log of 5/3. All right, so what we need to do is figure out the area under the curve, and this is a little bit tricky, okay, from 0 to 4. So literally what I'm going to do, okay, I admit this is tricky, is I'm going to figure that out with a definite integral. I want to know from 0 to 4 of this function here. 5e to the negative x over 3 minus 3. That will give me the area under the curve. And we actually know how to do this. So we need an antiderivative here. Okay, so the antiderivative is going to be 5e to the negative x over 3. But then we need to compensate for the chain rule. So we need to divide this by negative 1/3. That is the same thing as multiplying by negative 3. Okay? Then the antiderivative of negative 3 is negative 3x. There's our antiderivative. And I'm just going to make it negative 15e to the negative x over 3 minus 3x. Now we have to plug in 4 and 0. Okay? So I'm going to bring that down here. I'm going to rewrite it. Okay? So now I'm just going to plug that stuff in. Okay? So I'm going to plug in 4, and I get negative 15e to the negative 4/3 minus 12 minus, let's see what happens when we plug in 0. When you plug in 0, e to the 0 is 1. So this becomes negative 15 minus 0. That's just nothing. So that's it. So the area under the curve is literally negative 15 e to the negative 4/3. Negative 12 plus 15 is plus 3. Okay, so that's the area under the curve, so to speak, from 0 to 4. Okay, but keep in mind, we started at 5. So f of 4, and I'm realizing this is weird looking, is 5 plus that garbage there, plus negative 15e to the negative 4/3 plus 3. And if you want, you can clean that up a little bit, but for the sake of time, I'm not going to add 5 and 3 together. All right, C. For that interval, right there, find the value of x at which f has an absolute maximum. Justify your answer. I mean, we can just think about this. Pretend we start here. We start picking up area. F gets bigger, 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 smaller, 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 smaller. So if we had to draw it, bigger, 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 boop, smaller, 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 smaller. It's pretty clear to me that that is, that right there is the max. Okay, we only need to find the value of x, and that value of x is what it is right there. They told us it's 3 natural log of 5/3. So it's that x equals 3 natural log of 5/3. And that is going to be our max right there. Okay.